नहमदुहु व नुसल्ली अला रसूलिहिल करीम अम्मा बाद फ़अऊज़ु बिल्लाहि मिनश शैतानिर रजीम बिस्मिल्लाहिर रहमानिर रहीम. Today's topic of discussion is skewed distribution and the Poisson's distribution. I am Dr. Fatma Jalal Chaudhary, and I am going to present the very topic under the very kind supervision of Professor Dr. Sarah Afzal. Now, agenda for today's discussion would likely be like introduction to the skew distribution and Poisson's distribution, the categorization of data distribution in a very summarized way, implications of both types of data distribution, that is the Poisson's and the skewed one, practical aspect covered, data presentation along with examples, recent updates, and MCQ session. Final tips and takeaways from our seniors. What would be the objectives for today's discussion? At the end of the presentation, the audience, I would like to be able to at least recognize different kinds of distribution, practical examples, along with presentation of different data sets, practical implications of both the modalities. Now, what is data distribution? Distribution refers to how data spreads across a range of values. It describes the arrangement of your data, whether it clusters around a particular value, is scattered evenly, or skews in one direction. It also provides an insights into the frequency or probability of specific outcomes that we are supposed to measure. Now, what are the types of data distribution? In statistics, based on the type of quantitative data, there are two types of data distribution: discrete data distribution and the continuous data distribution. To quote an example, Poisson's is a type of discrete data distribution. Now, coming on to our first discussion, that is the skewed distribution. As you can very well see here, a graph which is being represented along the x-axis and the y-axis. There is a single peak here on which we can see the data distribution maximally distributed. In the upcoming terms, we are going to find what the value here would be, like the mean, median, or mode. Now, coming on to the skew distribution in probability theory and statistics, skewness is a measure of the asymmetry of the probability distribution of a real valued random variable about its mean. So, in this particular chart or graph, you can see that there's the mean, which is the highest most point, along with which the either the values are distributed in a positive skewness form or a negative skewness form. That means either they are inclined towards the left or the right. So, but we are supposed to measure the asymmetry of the probability distribution of a real valued random variable about its mean. The skewness value can either be positive, it could very well be a zero thing as well, it could be a negative, or it could even be an undefined value. Now, what is a unimodal distribution in which we are supposed to look at the skewness of the data? A distribution which is having a single peak, as in the previous example, we have seen that we have only a single peak there. Negative skew commonly indicates that the tail is on the left side of the distribution, and positive skew indicates that the tail is on the right, in cases where one tail is long but the other tail is fat. So in the positive skew, one tail would be the longer one, and it would be mostly be falling into the skewed distribution. The skewness does not obey a simple rule. For example, a zero value in skewness means that the tails on both sides of the mean balance out overall. This is the case for a symmetric distribution, but can also be true for an asymmetric distribution where one tail is long and thin and the other is short but fat, as in the positive skewness. Thus, the judgment on the symmetry of a given distribution by using only its skewness is risky. The distribution shape must be taken into account. In the upcoming slides, we'll be taking another important and interesting fact about the skewness of the data. So within each graph described in and then upcoming slide, the values on the right side of the distribution taper differently from the values on the left side. These tapering sides are called tails, and they provide a visual means to determine which of the two kinds of the skewness a distribution has, either a positive one or a negative one. So, skewness of a distribution is explained here as you can see along the x-axis and along the y-axis. There should be a mean, there should be a mode, and a median. From starting from the zero side on the either side of the distribution, we'll have a peak there. And if most of the values are concentrated towards the left side, it would be a negative skew. Whereas if it would be tapered towards the right side, it would be a positive skew. It would be a fat tail there. So negative skew, the left tail is longer. The mass of the distribution is concentrated on the right of the figure. That means the chart. The distribution is said to be left skewed, left tailed, or skewed to the left, despite the fact that the curve itself appears to be skewed or leaning to the right. So left instead refers to the left tail being drawn out of the mean or median, and often the mean being skewed to the left of a typical center of the data. A left skewed distribution usually appears as a right leaning curve, as we have observed in the previous slide. So positive skew, the right tail is longer. The mass of the distribution is concentrated on the left of the figure. So most of the values would be lying toward the left of the graph. The distribution is said to be right skewed, right tailed, or skewed to the right, despite the fact that the curve itself appears to be skewed or leaning to the left. Right instead refers here to the right tail being drawn out of the mean, and often the mean being skewed to the right of a typical center of the data. So a right skewed distribution usually appears as a left leaning curve. Now, an interesting fact about the skewness of data is skewness in a data series may sometimes be observed not only graphically but by simple inspection of the values. Uh, for example, or for instance, consider the numeric sequence 49, 50, and 51, whose values are evenly distributed around a central value of 50. We can transform this sequence into a negatively skewed distribution by adding a value far below the mean, which is probably a negative outlier. For example, 40, 49, 50, and 51. So here the 40 is the outlier. Therefore, the mean of the sequence becomes 47.5 and the median is 49.5, which is very much near to 50 or 49. Highest and mean and median. Based on the formula non-parametric skew, the skew is negative. Similarly, we can make the sequence positively skewed by adding a value far above the mean, which is probably a positive outlier, for example, 49, 50, 51, and 60, in which case 60 is the positive outlier, where the mean is 52.5, which is far above the 50, which is the highest value, and the median is 50.5, which is again above the highest value. So, what is the relationship between mean, median, and mode in a skewed distribution? In all of the cases, we can safely say that mean, median, and mode coincide in a skewed distribution at some point above or at the point of 0. So in this case, as we can observe that mean is 5.07, variance is 2.4, and standard deviation is 1. Skewness in this case is 0, and non-parametric skew is equal. That means all of the values are evenly distributed around a skew distribution. So this is an example of asymmetric distribution with 0 skewness. So in the cases where we don't have a zero skewness, what would be the case? In the symmetrical, in the middle of the figure, you can see there is a symmetrical distribution in which the center point of mean, median, and mode are coinciding with the two peaks of equal tail distribution on the both sides of the curve are going. Whereas in positive skew, you can see that a mode is the median point. Median a bit tapered off at the positive side, and mean is still far beyond that. So positive skew would be representing a mode as the median point or the highest point of data distribution, whereas other points would be following later. In the negative skew distribution, you can again see that mode is the highest point, median is following the negative skew downwards, and mean is making it further skewed towards the negative side. So, for simple example, if we have to get a skewed distribution afterwards, then we will draw a curve here. In the distribution of adult residents across the US households, the skewness of the distribution would be toward the right. However, since the majority of cases is less than or equal to the mode, it is basically 1500 to less, I guess it would be around 1200, which is also the median. So mean sits in the heavier left tail, as you can see. Mean would be here, somewhere between 1.8 to 1.9. So the mean sits in the heavier left tail. As a result, the rule of thumb that the mean is right of the median under right skew fails. So this is the interesting fact about the skewness of the distribution. So what are the applications for the skewed distribution for data? Why are we concerned about the skewness of a data and what we can get out of it? Skewness is a descriptive statistics that can be used in conjunction with the histogram and the normal quantile plot to characterize the data or distribution. Skewness not only indicates the direction and relative magnitude of a distribution deviation from the normal distribution, but with pronounced skewness, standard statistical inference procedures such as confidence interval for a mean will be not only incorrect in the sense that the true coverage level will differ from the nominal, for example, 95% level, but they will also result in unequal error probabilities on each side. So pronounced skewness would be mostly concerned with the data coverage level error probability. Skewness can be used to obtain approximate probabilities and quantiles of distribution, such as value at risk in finance via the Cornish-Fisher expansion. Many models assume normal distribution, that is, data are symmetric about the mean. The normal distribution has a skewness of 0, but in reality, data points may not be perfectly symmetric. So, an understanding of the skewness of the data set indicates whether deviations from the mean are going to be positive or negative. So, outliers above or below the mean or the mode are mostly considered. So, D'Agostino's Chi-square test is a goodness of fit normality test, which is based on sample skewness and sample curtices. What are the other measures of skewness? As you can see here, the colors are marked for the mode, median, and mean with this alpha value of 0.25, alpha value of 1, and they are distributed in a skewed manner. So, two log normal distributions with the same medians and different skewness. These are basically other measures which are to be discussed in upcoming slides. These are basically the alpha values to be considered for the Pearson's correlation. So Pearson's first skewness coefficient or mode skewness. The Pearson mode skewness or first skewness coefficient is defined as mean minus mode over standard deviation. And Pearson's second skewness coefficient or median skewness is defined as 3 into mean minus median over standard deviation whole over standard deviation, which is a simple multiple of the non-parametric skew. So if we are stuck with the simple skewed distributions, we can use Pearson's first skewness coefficient or second skewness coefficient. Along with that, there are multiple other available parameters also there for the skewed distribution, which are rather difficult for us to understand at this stage. So Poisson's distribution, coming on to the next type of data distribution. In probability theory and statistics, the Poisson's distribution is a discrete probability distribution that expresses the probability of a given number of events occurring in a fixed interval of time if these events occur with a non-constant mean rate and independently of the time since the last event. It can also be used for the number of events in other types of intervals than time and in dimensions greater than 1. For example, the number of events in a given area or volume. The Poisson distribution is named after French mathematician Simon Denis Poisson. It plays an important role for discrete stable distribution. So this is an example of a Poisson's distribution. As you can see, we have lambda, which is equal to 1 in the orange state, lambda is equal to 4, and lambda is equal to 10 in the blue state. So in all of the cases where we are to get a Poisson's distribution, here the k value is running and it's the lambda one. So in all of the cases where we are concerned with the skewed distribution, it should be a integer. It should be a number with a definite value like 0.0, 0.05, 0.1, 0.152. So horizontal axis, the index k, the number of occurrences which are represented by 0, 5, 10, 15, and 20. Lambda is the expected rate of occurrences. The vertical axis is the probability of k occurrences given in the lambda time. So the function is defined only at integer values of k. The connecting lines are the only guides for the I. So if we don't plot them, even then we can see the data distribution along the graph. Now this is the cumulative distribution function, which is here to explain with you that mostly the data is represented in the simple integer forms. Here the lambda is 1, 4, and 10 respectively. K is at like 0, 5. So here we can see that the lines are uninterrupted and they are not being traced to follow a simple sequence pattern because they are mostly not represented by integers like 0.2 to 0.4. It would be somewhere between 0.38, 0.41, likely 6.1, then 7.8 or 7.6. So this is a cumulative distribution function, which is also a function of the Poisson's distribution. So how are the values presented in the Poisson's? Mean is represented as lambda. Median is equals to almost equals to lambda plus 1 over 3 minus 1 over 50 lambda. Mode is represented as lambda minus 1 and lambda. Variance lambda and skewness 1 over lambda. So the Poisson distribution can be applied to the systems with a large number of possible events, each of which is rare. The number of such events that occur during a fixed time interval is, under the right circumstances, a random number with a Poisson distribution. The equation can be adapted if instead of the average number of events, where the lambda is equal to RT, where T represents the time. So P is the k events in interval T. So this is the equation for our Poisson distribution. So to quote an example, the Poisson distribution may be useful to model events such as the number of meteorites greater than 1 meter diameter that strike Earth in a year, the number of laser photons hitting a detector in a particular time interval, the number of students achieving a low and high marks in an exam, and locations of defects and dislocations in materials. So as you can see here, we have a picture which is basically marking a chewing gum on a sidewalk. The number of pieces on a single tile is approximately the Poisson distributed. So you can see it is in a time interval and it not in a fixed frame, but you can basically measure the number of events which are taking place in a time interval. So what are the assumptions and validities for a Poisson distribution? The Poisson distribution is an appropriate model if the following assumptions are true. K is a non-negative integer, is the number of times an event occurs in an interval. The occurrence of one event does not affect the probability of a second event. The average rate at which events occur is independent of any occurrences. Two events cannot occur at exactly the same instant. If these conditions are true, then K is a Poisson random variable, or it is to be accepted as a Poisson random variable. The distribution of K is a Poisson distribution. So Poisson distribution is also the limit of a binomial distribution. As we have discussed in Skinner's, it's a unimodal and uninomial distribution unimodal, for which the probability of success for each trial equals lambda divided by the number of trials, as the number of trials approaches infinity. To quote an example, it has been reported that the average number of goals in World Cup soccer match is approximately 2.5, and Poisson model is appropriate because the average event rate is 2.5 goals per match. Lambda would be equal to 2.5. So P is the K goals in an event or match 2.5 K E minus 2.5 divided by K epsilon. So this is how we are going to calculate the Poisson distribution for that very match. So examples for the special circumstances: once an interval events, the special case of lambda is equal to 1 and k is equal to 0. Suppose that astronomers estimate that large meteorites above a certain size hit the Earth on an average once every 100 years. Lambda is one event per 100 years. So this is how we are going to calculate the p, which is approximately 0.37. Under these assumptions, the probability that no large meteorites hit the Earth in the next 100 years is roughly 0.37. The remaining 1 minus C7, which is equal to 0.63, is the probability of 1, 2, 3, or more large meteorites hit in the next 100 years. In an example above, an overflow flood occurred once every 100 years, in which lambda is equal to 1. The probability of no overflow floods in 100 years was roughly 0.37, again by the same calculation. So, what are the properties for a descriptive statistic? The expected value of a Poisson random variable is lambda. The variance of a Poisson random variable is also lambda. The coefficient of variation is lambda 1 minus minus 1 over 2. So it is the index of dispersion taken is 1. So this is how we are going to calculate. Now, what are the applications? Some applications of the Poisson distribution to count data. Number of events are telecommunication, telephone calls arriving in a system, astronomy, photons arriving at a telescope, chemistry, the molar mass distributed, management में customers arriving at a counter or call center, finance and insurance, number of losses or claims occurring in a given period of time. Seismology, asymptomatic Poisson model of risk for large earthquakes, radioactivity decays, and optics, number of photons emitted in a single laser pulse. Upon coming to the conclusion, we have to do a number of other calculations which are above and beyond our scope, and they are very complex sort of calculations. Law of rare events, for example, cited here. The rate of an event is related to the probability of an event occurring in some small sub-interval of time space, or otherwise, in the case of Poisson distribution, one assumes that there exists a small enough sub-interval for which the probability of event occurring twice is negligible. With this assumption, one can derive the Poisson distribution from the binomial 1, given only the information of its expected number of total events in the 4 interval. So interpreting the graph is very complex sort of thing, and for which we have to use other softwares as well, like MATLAB or Fortran and Gamma functions, which are above and beyond our scope. So what are the recent updates in the skew distribution? We have this section, peer-reviewed article, which says a multi-model alpha skew normal distribution, a new distribution to model skewed multi-model observation. FX says multi-model alpha skew normal MMASN distribution is proposed for modeling for the presence of multiple modality at arbitrary points. So with the alpha skew normal distribution of Ilal Oliveira, which is cited in 2010, cumulative distribution function CDF, moment, skewness, and courtesies of a proposed distribution are derived in the compact form. The data modeling ability of the proposed distribution is checked by considering three multi-model data sets from literature in comparison to some nested and known distributions. Ekaki information criteria, which is AIC, and the likelihood ratio, which is LR test, both clearly favored proposed model over its nested models as expected. So recent book chapters on skewed distributions, and this is a recent chapter on the histogram, which says that skewed distribution and data transformation. A skewed distribution is neither symmetric nor normal because the data values trail off more sharply on one side than on the other. So in the business and other sort of forms, we can apply it. Probability and related concepts in the skewness. Heavy tail distributions are one source of concern when employing conventional statistical techniques. So with the skewed distributions, one or more of the fundamental issues can be described here as to whether the mean is a good choice. Consider, for example, the distribution shown is skewed to the right. In this particular case, the population mean is located in the extreme right portion of the curve. In fact, the probability that an observation is less than population mean is 0.74 through the calculation. So for the Poisson distribution, the recent update added is the properties and application of Poisson distribution. Poisson distribution is not only a very important distribution in probability theory, but also a useful tool to study the random events. Firstly, this paper gives a simple introduction of Poisson distribution and some characteristics of Poisson distribution. Secondly, some properties of Poisson distribution are introduced and proved. In the end, some applications of Poisson distribution are introduced, such as the application in the rare events and in daily life. We also do some analysis about the application of Poisson distribution. There was a number of calculations there which were very complex. Modeling biological uncertainty using the double fuzzy Poisson distribution. It is another paper. Abstract says this paper introduces a novel probability distribution, the double fuzzy Poisson distribution designed to address two levels. So coming on to the MCQ session, MCQ number 1 says which of the following best describes the skewed or negatively skewed distribution. The distribution has a long right tail, distribution has a long left tail, the mean is greater than the median, the distribution has a peak on the left side, and distribution has a double-sided peak. Which could be the right answer? Yeah, the answer is B. The distribution has a long left tail. So coming on to MCQ number 2, which of the following is not a characteristic of a skewed distribution? The emphasis is on not. The tails of the distribution are not equal in length. The mean is typically not equal to the median. The distribution can be either positively or negatively skewed. The variance is always greater than the skewness, and mean, median, and mode always coincide. So here the variance is D. The variance is always greater than the skewness. So answer would be D. MCQ number 3. If the distribution is positively skewed, then which of the following is most likely? The mean is less than the median. The mean is equal to the median. The mean is greater than the median. The distribution has two peaks. They can't be represented graphically. See? Yeah, the mean is greater always. So MCQ number 4, in a negatively skewed distribution, which of the following is true? The mean is greater than the median, the mean is less than the median, the mean is equal to the median, the variance is 0, the probability is nearly 0 in each of these cases.
B.
Yes, answer is B. The mean is less than the median, because and this is how we are going to get a negative skewed curve. MCQ number 5, a right skewed distribution has a longer left tail, a longer right tail, a symmetric shape. The mean greater than the median, there is a 0 probability for any such kind of distribution.
Alpha.
D.
Yeah, answer is B, a longer right tail. A right skewed distribution, longer and fat left right tail. Sorry. MCQ number 6, which of the following statements best describe the Poisson distribution is false? The distribution is always positively skewed. The distribution is used for rare events occurring independently over a fixed interval. The Poisson distribution has no upper bound on the number of events. The mean and variance are equal. There is a probable chance for no such event in real time to be graphed. A, the distribution is always positively skewed. Because it's a false statement, it could either be positively skewed or it could be negatively very well skewed, or if it's a non-integer number, it could never be drawn well. The Poisson distribution is mostly following which of the used for which of the following models: the height of people in a population, the number of emails received in an hour, the time it takes for a computer to complete a task, the income distribution of a population, or total GDP of a population. On which we can apply the Poisson distribution. Height of people in a population, no time involved, computer to complete a task with the known number of events, the income distribution, so the number of emails, the events, and received in an hour, the time period defined. So the answer is B. MCQ number 8, what is the mean and variance of the Poisson distribution with parameters lambda 7 and variance 7, lambda is equal to 7. So mean would be 7, variance would be 7. Mean would be 7, variance would be 14. Mean would be 14, variance would be 7. Or mean would be 14, variance would be 14. Mean minus 7, variance would be 14. So what could be the answer here? It's 8. The answer, mean and variance are always equal in a Poisson distribution curve, as we have earlier. So mean and variance are both equal to lambda. This is the solution. So MCQ number 9, if the average number of calls to a call center per hour is 5, what is the probability of receiving exactly 3 calls in an hour? 0.14, 0.17, 0.20, 0.083, 0.00501. So for this, we have to apply the equation which we have discussed earlier. So I guess that would be the Poisson distribution formula P x equals to k, when so where lambda is equal to 5 and k is equal to 3. So solution would be according to that, the A choice would be fine. MCQ number 10, which of the following is a characteristic of the Poisson distribution? The events occur with a known average rate in a